Okay, we're going to do this homework problem first. So I'm going to switch to the camera here to the, I should have this open. Okay, this is where we left off last time. We said that for a vibrating body with an elastic restoring force, we can calculate the frequency or the period. Now these are just reciprocals of each other. And you can see that they're reciprocals of each other because here we have 2 pi in the denominator. Here it's in the numerator, and these are reciprocals too, right? So for this problem 33, it says a 400-gram mass will go down 20 centimeters on our spring. So if it goes down x equals 0.20 meters, this force is going to be mg, right? And we know our spring constant K is in what units? Newtons per meter, right? So if I do this, my weight in newtons, this would be 0.4 kilograms, 9.8. So to get newtons per meter, 0.4 times 9.8, I'll do our newtons. .2 meters. So it looks like our spring constant is 19.6. So now we use that same spring. We put a different mass on it and pull it down, and we know then the period is 0.1 seconds. It wants to know what the mass is. So my period is, from our equations, 2 pi times the square root of m over k. Now, if I need to solve this for my mass, I'm going to square both sides to solve it. I'm going to get my period squared equals 4 pi squared m over k. Now I can solve that for my unknown mass. And that should work out pretty slick. Okay. Let's continue where we left off, and this will explain the lab tomorrow as well. So we are going to be on this page. Tomorrow for lab, we're going to do a pendulum, and we're going to calculate G out of it. And we'll look at that. If we have a pendulum, and if you pull it back an angle that is less than 15 degrees, not a lot, these equations are valid. For our frequency, it's going to be 1 over 2 pi times the square root of g over L. That, of course, is gravity. This negative, if you use negative 9.8, it's going to make it positive. We have to have a positive square root radical, obviously. This is just the length of our pendulum. So tomorrow, you're going to take some fish line. One of you is going to have to stand on the table, whoever's tall enough to reach up and tie a string through the ceiling tile framing. We are going to hang something like this, and we'll send this in motion like our diagram. Then you're going to cut off, once you've got it hanging there, you want this to be almost the bottom of this within an inch from the floor. That will be your original length. Then, in this equation, we're going to change the length. We'll cut off 1.5 feet or so, send the pendulum in motion. We're going to measure the period here. This is in seconds, right? Seconds per revolution. And what you're going to do is you're going to time 10 revolutions. So it's going to be the number of seconds divided by 10. Because you don't want to let this, you don't want to try to just do one back and forth. You're not going to get good data. So wherever you're going to start, you can look at it straight down in time from the center. You can look at it sideways, and maybe you want to start and stop where it's at this high point here on this side or this side. Whatever you do, you're going to time it for 10 revolutions at each length. And we want 5 to 8 lengths. So if we do this for lab, it's going to look like this. We're going to have our period is equal to 2 pi times the square root of L over G. Yeah, you can put a negative in there. If you put, we have to put a negative, use negative 9.8. But we'll keep the negative out, keep it clean. Now notice what is not in this equation. This is not in our equation, right? There's no mass in our equation, and there's no angle in our equation. So it doesn't matter if you pull it back 5 degrees, 10 degrees, 15 degrees. So I want to show you that first. I think I got the right video on the desktop here. I pulled some videos. I thought I pulled some videos. Remember that comment I made about redoing the recording? Looks like, man, I swear I pulled it.
I see a final exam. Hey Ron, I think you're all enough.
Let's try this. Yeah, but watch happens here.
Here is a periodic motion that's very familiar. Watch what happens here when we triple the mass, double the pendulum more or less.
Now, if you double the mass,
Period of pendulum does not depend on the mass vibrating. It depends on the length of the pendulum.
now watch this sideways here.
Even as everyday example on a playground, you can the law of physics in action. The time it takes to swing back and forth one only depends upon the length of the chain and of the split.
The first one was kind of better. Right there looks pretty close, right? So it doesn't depend upon the mass. It doesn't really depend upon the angle, because this first person's swinging a longer angle, correct? All it depends upon is the length. I did my swing like this, but realize this person's going to swing a little crooked because this rope on right here is a little bit lower on the branch than this one. It does make a difference. I thought I had the Tacoma Narrows Bridge on here. Where is it? There it is. So everything has 1940. 1940? Dude, we didn't even get in World War II yet. Korean War. You got a pretty good wave here. Standard frequency. I know blacktop is really flexible. Yeah, so I don't know, like, I learned the hardware because I had to take my bridge apart from my driveway, and I sliced it with a cement saw. So I had slices about 2 feet wide, and I went underneath them with a great big bar to lift them up, and it basically bent like a marshmallow. Blacktop will flex and bend, and I'm not sure. Well, eventually it does here, but I'm not sure if it's blacktop. It can flex pretty well. Yeah, you would think the concrete here. Yeah, this is real time. So this thing is. I can't remember what. I think this is only 6 months after it opened. I think. There's a car right here. Yeah, there's a person walking right here, I think, isn't there? Finally, but I think it lasted 6 months was all, if I remember right. But I'd have to look. Okay, so for lab, we're going to solve this. We're going to try to figure out our gravity by changing our lengths. So if we're going to figure out gravity, we're going to square both sides, and we're going to end up with the period squared is equal to 4 pi squared L over G right? If we square both sides. Now, then if we do t squared divided by L, we end up with 4 pi squared over G, right? We're just moving L down below. So here's what we're going to do. We're going to graph this. This is going to be my changing Y. This is going to be changing X. So if we put period squared on the Y-axis, our different lengths on the X-axis, changing Y over changing X, what do we have? We got slope, right? So we're hoping we're going to graph 5, 6 different lengths here. We should get a straight line, right? This is going to be period squared on the Y. So what's my units going to be? And on the X is going to be length. So this is meters, right? So your slope is going to equal to 4 pi squared over G. So if you solve this for G, realize we can just switch these around, right? When you solve this for G, it should be 4 pi squared divided by your slope. No, no. I can never trust G. Never trust G. Brings havoc all the time. Breaks a lot of grandmothers' hips. Can't trust it. Yeah. So hopefully, now, we should get pretty dang close. I'll show you the results here of a lab. So they've got, this should be in meters, right? So this is a sheet I'll give you. They've got, we did 10 cycles, right? You're going to time it 3 times, average it. So this is going to be the average for 3 cycles. So if we divide this by 10, this would be our period here. This is simply our period squared. And then we just got to graph period squared here on the Y. Length here on the X. Here's our slope. Now, do you remember how to get this equation? Just right-click on one of these points. Format trend line and display equation on chart. And here's the slope. So they got 9.7, not bad. And here's our equation, here's our percent here, less than 1%. Not bad. So tomorrow I'll give you a sheet. You can fill this in, graph this, hopefully. You are about 1% maybe, huh? Should work out pretty well. Okay, so let's look at this example. Measuring, oh, here we got a problem already on this. Huh. Will the acceleration of gravity with a simple pendulum having a length of, that seems like an awful long period. So let's get this in meters. Our length here is, how many meters? 0.75 meters. And this is our period. So I'm going to go ahead and square this right away. Period squared is equal to 4 pi squared L over G. So if we solve this for G, again, G is going to equal to, we can just switch these around. G is going to equal to 4 pi squared L over the period squared. One 0.7357 seconds. And I'll actually punch this in. 4 times pi squared times 0.75 divided by 1.7357 squared. 9.83. Okay. We are not going to do this slide. So we can cross this slide out. This slide here just would prove again that circular motion. If you did a shadow down here and ran this paper roll through, you'd get a sine wave, right? If you graph the shadow, but so we can get rid of this slide and we can get rid of this slide. And we are not going to do a torsion pendulum, so we're on mechanical wave. So for mechanical wave, we just need a disturbance in an elastic medium. Now, we'll show you a video. We can have a transverse wave and we can have a longitudinal wave. So in a transverse wave, the individual particles of medium is per. You've got a wave like this and you've all done this and the direction of the wave is this. Obviously, this is perpendicular, right? We'd have a 90-degree angle. So you've done this with ropes or something where you've sent the wave down. What's the wave do when it gets to this end?
There's that wall.
Yeah, if this is a wall, it's going to come back opposite. I'll show you some video clips of that. It should. In a longitudinal wave, the vibration of the medium part parallel to the direction of the wave. So here you would send this thing down like a slinky. So I'll show you a couple video clips, I think, right here.
And possibly, though, the directions that you tested. These are called longitudinal moves. And they can also be made waves by wave. These are called transverse waves. Order waves are a combination of longitudinal and transverse wave motions. Each bit of color on the surface moves around in a little circle. Each circle is the alphabet of the name. Altogether, giving familiar articulation of the free surface. There's a simple eight movement. Let's watch it slowly. What you see is called a train of waves.
So they're at 0G then? The only way, they have to be at 0G because this slinky's not basically sagged right here, right? Now, if you can get a standing wave, there we go. You've all done something like that with something, I hope, where you can get a standing wave.
This different parts of a longitudinal wave. Rarefaction is where the individual coils are far apart, and compression is when the coils are close together.
It's essentially a sound wave, where your air is close together and then far apart. Oops. Okay.
Mechanical waves or impulses pass through a crystal from atom to atom because each atom is bound to an equilibrium position by electrical forces. When disturbed, they act mechanically, exactly like masses connected by spring. When an impulse moves through a crystal, no single oscillator is very far, but the disturbance moves right along.
Now you increase frequency of the wave, that should make more waves per second. The shorter the wavelength becomes.
When any stable mechanical system is disturbed, nature's response is simple harmonic motion. For a single oscillator, that's a specific. But when oscillators blink, one, next, and to the next, disturbance in one passes up to the next, and continues on down the line.
Okay, let's go to our next slide here. This should just be review. This is our speed is equal to wavelength, frequency times wavelength, or you could do V is equal to wavelength divided by the period, right? Either way. Nope. Period. This is our period. This would be our period in seconds per revolution, right? It's just going to be seconds. Now let's see if I have that quiz up yet. Yes. So look at this though. Look at all of these. I'm going to make this bigger. All these waves. Remember we did radio waves. We calculated the wavelength of FM, less than 10 feet. AM, about a quarter mile. You've got radio waves up here. All of these have the same speed. 3 times 10 to the 8th meters per second. Obviously, if they have the same speed, what's different is frequency and wavelength. What do you see though? You turn your microwave on, do you see those waves zapping your food? Do you see radio waves coming to your car antenna? Do you see when you hit the remote control? Do you see that wave beam go into your TV or whatever you're trying to record or change the channel? Do you see those rays that give you sunburn? You get an x-ray, do you see those rays come into your body? No, the only short amount of frequency and wavelength you see is actually visible light. Is this right here. This is the visible spectrum that you see. You can see this right here is 380. If you went backwards, this would be Roy G. Biv, right? Going backwards. You can see this right here is in nanometers. 380 times 10 to the minus 9. So that's what I have for a question here for nanometers. This is all we see, just this visible spectrum. Again, all of these are the same speed, 3 times 10 to the 8th meters per second. You know, I don't know. I know they say what deer are colorblind, right? So they don't see color. Humans are colorblind. I mean, I had one student that couldn't see anything in here. All they saw was gray. So I'm not sure. I'm sure there's probably some difference, just like there's different sound frequencies that dogs can hear versus humans. There's probably some difference, but that I don't know. Okay, so if we do this question here, again, these ocean waves are a combination of transverse and longitudinal. Calculate the velocity of a wave propagation, a gull in the ocean. The distance between crests is 10 meters. Then that is a wavelength, isn't it? Our wavelength is 10 meters, and that gull goes up and down in 5 seconds. So if that's 5 seconds, that's a period, right? So the velocity of our wave, we'll do frequency, or excuse me, wavelength, because I know this is in meters, divided by my period, because I know that's in seconds. So in this case, we'd simply have 10 meters divided by 5 seconds, and we're going to get 2 meters per second. Now, our next example of waves is this. And you could do this with string, but most people do this with wires, right? So if you have a wire tied to a wall and you run it over a pulley and you put a weight to it, and if you pluck the string here, the sound that you hear or the frequency of vibration probably depends upon how much weight's on here, correct? Or isn't tightening or loosening the strings. And if you have a guitar, what's the easiest way to tune it? You just download the app Guitar Tuna. Anybody use Guitar Tuna? No, you don't take it to a store. It used to be complicated to tune these damn guitars because you'd have to, if people could listen, they can hear it, but Guitar Tuna, well, you hire Mr. Zahn from Pepin, Wisconsin. He'll come and fix your piano. And the problem is those guys that are listening with their ears, that you're hitting 3 strings at once. That hammer on a piano, it's not hitting 1 string, it's hitting 3 strings per hammer. It's those guys that can do that. I know Zahn can do it out of Pepin. He's phenomenal. But Guitar Tuna is awesome. Now, you can buy, if you have kids or whatever you got, you can buy a guitar dirt cheap. You can get from China on eBay for 99 cents colored strings. They're metal strings, all different colors. Throw that on a guitar, download Guitar Tuna, it's free, and you can tune the darn thing in no time. You just pluck the string and it gives you a thing up or down, and you just tighten it. So obviously then, our velocity should depend upon the force, and this is our mass of the string per unit length is our constant down there. So this is just like a spring constant, only for this string it's mass per unit length. So in this case, the length of a string in the above is 2 meters. So this is an L in here. We got a mass of 0.0003 kilograms, 0.3 grams. Calculate the speed. And the force is, the tension force would be 20 newtons. Now this would be easy to do. If you have 20 newtons, divide by 9.8, that would be how many kilograms? You just need to hang on here, correct? It'd be simple to get that number. So what do we got here? We'll just use the second equation. We've got a mass, we've got a length. So we can use our velocity is going to be the square root of our force divided by mass over length. And all of our units are correct. Yeah, we've got meters, we've got newtons, we've got kilograms. No. What's that? No, F is actually our force. It already gives it to us in newtons. It would be this force of weight, really, in this example. So we already have this force in newtons. Yeah, it's a mass per unit length of the string. So you could cut off 2 meters of this string and mass it, and you should get 0.3 grams. So you have a mass per unit length, you have a force. We should be able to get a velocity of this, and if we do this, 20 newtons over 2 meters divided by 0.0003 kilograms. And we got to square root the whole thing. Now let me show you how to punch this in. I would do this in my calculator. I would do that bottom fraction first. I'm going to go, 2 divided by 0.0003. I'm going to hit enter. Yeah, well, yeah, well, of course, yes, yes, of course, yes. Kilograms, 2 meters. Yeah, you could flip, you could actually go, you can actually flip it right away and go the force times 2. But just looking at this without knowing how to flip that reciprocal, I'm going to take my 0.0003 divide by 2, I get this. Now I'm going to take 20 divided by the answer, so I got to hit second answer, enter, and now I want the square root of that, so I'm going to go caret 0.5, and I get 365. Okay, now, last thing we're going to look at are some video clips, and this is on your quiz, and this is called superposition. It's basically interference, constructive and destructive interference of waves. Now, if you have the Bose noise canceling headphones, this is what they're doing. There was a company called Anti-Vibration and Noise Canceling Technologies. I think they're in Colorado. I invested in them originally. That's where they got the patents for the Bose headphones. They were going to make vacuum cleaners that were silent, pretty silent, because they were going to put out a counterwave. These vacuum cleaners are loud, right? And they had an agreement with Walker Muffler to electronically put out a counterwave. So you're either going to have constructive or destructive interference, and I got some videos here too. Well, I actually have tuning. Okay, this, if you look at these two waves coming together, this is going to be constructive interference. Watch what happens. These waves are adding together, correct? Every position of this wave is adding together. That's what it looked like when it went over top of each other. And notice they transfer through. They continue through. They are not canceled. They're adding, correct? So this is constructive interference. If you take this part of this wave and add it to this part of this wave, you're going to get that height. But when they're directly over top of each other, you get that, right? Again, they will travel through. Now what's going to happen? Almost canceled right there. I couldn't stop it perfectly, but they cancel each other, correct? But they travel through. What's going to happen when these get over top of each other? They're going to add together, correct? Travel through, added together. What's this going to do? But back here is your noise canceling headphones. Where did I have it? Right there. Cancel, right? Wouldn't that be nice? Flip a switch, somebody's talking to you. You don't want to hear them, just flip a switch. Registers their frequencies of their voice, sends out a counter wave, makes them dead silence to you. You can do the same thing with slinkies. If it shows up here. Oh. These two are going to meet, add up, right? One in the middle is going to cancel right about here, right? Cancels. Okay, let's see what you can do for homework. You can get, here's pendulum problems. Looks like we can finish 16 for problems, because we're done with 16. So you can finish 16 problems. And then on the quiz, let's see where we can get to on the quiz. Through 11. You can do the quiz through 11. All right, we'll do chapter 17 starting on Wednesday. Lab tomorrow. I'll send out the lab where you can just zap it, print it, staple it, 3-hole punch it in the back. What's that? I don't know. Not this week. Yeah, pretty much.